Hello, everybody. It's 12:25. It's Thursday afternoon. Hope you're doing okay. This is the last recording I'll make here. It's our worksheet 13, number 1, question 1. Find a power series for that function, x over 1 plus 2x, centered at 0, using a known power series, and then give the radius. Okay, so it says use a known power series. So these are our known power series on our formula sheet that is provided to you on the exam. And x over 1 plus 2x can be adjusted into the form 1 over this one here, 1 over 1 plus 2x. So let's do that. And then that would be for the series 0 to infinity, x to the k, or input to the k, and then size of the input less than 1. So let's let's write this as x times 1 over 1 minus negative 2x. Then that is equal to x times the series 0 to infinity input to the k, input, size of the input less than 1. All right, so then we need to do a couple things. When you write your series, if you have extra x's out there, you need to bring them in here and include them with this x or combine them with that x. If you have exponents here, you need to apply them to the x and to the negative 2. So we would have the sum 0 to infinity, negative 2 to the k, x to the x, and then x to the k. That's x to the 1. And when you combine those, that's x to the k plus 1. K plus 1. Then that's our series. So this goes there. There we go. And then for the interval of convergence, so the absolute value bars would make that negative 2 a positive 2. Then you divide by 2, and that tells you x is between negative 1/2 and 1/2. And the benefit of using your known power series, that known one over here, 1 over 1 minus x, is it tells you more about the interval. It tells you that the endpoints are excluded because it's strictly less than 1. So here, our endpoints are going to be excluded. We're going to be open. X will be strictly less than 1/2 and strictly bigger than negative 1/2. You do not need to check endpoints with the ratio test, or sorry, not with the ratio test, but by plugging them back into the series. Now, if using this known form, if we had differentiated or something in here along the way, to find the known form, then when you differentiate, you lose that property. It's not necessarily whatever property the endpoint currently has, whether it's excluded or included, you lose that, and it might remain included, it might remain excluded. It just depends. You'd have to check them again. Here, our interval is negative 1/2 to 1/2. The radius is 1/2. Then x cubed cosine x squared. Here's your table. Cosine x squared. Cosine of an input is negative 1 to the k, input to the 2k over 2k factorial all x. So here our input, we would have x cubed times series, and I already forgot, 0 to infinity, negative 1 to the k input. So x squared to the 2k all over 2k, all of that factorial for all x. So, whoops. Okay, so for the all x part, for your interval is all x, or negative infinity to infinity, so the radius is infinite. Then when you bring the x cubed in, we're going to get the sum 0 k 0 to infinity, negative 1 to the k x. Let's see, this here is 4k. You're going to multiply the 2 and the 2k. So 4k plus a 3 is 4k plus 3. It is not 7k. So 4k plus 3 over 2k factorial. That's that one. Keep going. Identify the function represented. Okay, so that power series looks a whole lot like this one right next to it. The only difference here is this is an x and this is a negative x. So take your series for x to the k, and anywhere there's a x, put a negative x. So that tells us the interval is all real numbers, and e to the negative x would be the function. E to the negative x. The next one's almost the same, except you're inputting a -1, not a negative x. So it's e to -1. Let's keep going. Okay, from the first non-zero terms, Taylor series. So with the center not being zero, you either need to adjust the known series to account for the center, or you need to use a Taylor series formula. Okay, so let's do both. Let's do Taylor series formula is Taylor series of a function f of x centered at x equals a. It's this one up here. And yeah, okay. So if we do that, we would have t of x series 0 to infinity, kth derivative at 2 all over k factorial x minus 2 to the k. And if we want the first four terms, so this is asking us really for a Taylor polynomial because it's just wanting four terms, not an expression for the entire series. But then it does say write the power series using summation notation. So let's go ahead and find the series. So we'll find the series and then use it to generate the first four terms. All right, so for the when you're using the Taylor series formula, you need to go calculate those derivatives. We need to figure out what the kth derivative at 2 would be. And to do that, you need to take derivatives. So original function of e to the negative x is itself, first derivative, second derivative, third derivative, fourth derivative. And you'll notice that all of those derivatives, so kth derivative at x, would be e to the negative x, but then they're all negative on the odd number k values, so -1 to the k, and we need the kth derivative at 2. So that's -1 to the k. We're plugging in 2, not for k, but for x. All right, so -1 to the k, e to the -2, -1 to the k, e to the -2. All right, that's what your numerator is. There we go. Then that's your series. There's nothing to really simplify there. So if we want the first four terms here, let's switch colors. First four terms would be the 0th, first, second, and third term. Or when k is the 0th term is the first term, and the first term is the second, and so forth. So when k is 0, we get -1 to the 0, e to the -2, 0 factorial, x minus 2 to the 0. And then plug in the same situation, except our k's become 1, and then 2, and then 3. So what do we get there? Okay, so -1 to the 1, e to the -2, 1 factorial, x minus 1 to the 1, plus we need some space. Let's make that smaller. All right, so those are our first four non-zero terms. Nothing saying to simplify there, so you could just list that, but I want to simplify what I can. So in the first term, we just end up with e to the -2 because everything else is a 1. Then minus e to the -2, x minus 1, plus e to the -2, x minus 2 squared over 2, minus e -3, x minus 2 cubed over 6. That is our all right, so those are the first four non-zero terms of the Taylor series. Non-zero because none of those are 0. And That's no different than the third degree Taylor polynomial for that function e to the negative x centered at 2. All right, so if we want the power series, then the power series is what we had up there. That's the sum 0 to infinity, not that. Sum 0 to infinity negative 1 to the k e to the negative 2 k factorial x minus 2 to the k. Then, right, yeah, from the radius and interval of convergence. Okay, so since we used the Taylor series formula, you would need to do the ratio test. So limit k to big negative 1 to the k e to the negative, oh, we need the k plus 1th term. So e to the negative 2. All right, then simplify those things. Let's see, the negative things, negative 1 to the k plus 1, negative 1 to the k, they're always 1 with the bars. K factorial over k plus 1 factorial gives us k plus 1. And the e to the negative 2's go away. So these are out. That's out. That's out. K plus 1 right there. This is out. That's out. X minus 2 to the k. X minus, there are k plus 1, many of them up here, k many of them down here. There's one more left in the numerator. So x minus 2. That limit is 0, which is less than 1 for all x. So your interval, negative infinity to infinity, radius is infinite. Now there's another way to do that, and that's, let's use another color. We could have adjusted for the center. So e to the negative x is the same as e to the negative of x minus 2 plus 2. That's the same. E to the negative of x minus 2 minus 2. That's e to the negative x minus 2 times e to the negative 2. And that is an e to the negative 2 times the sum 0 to infinity e to the negative 2. Here, let's put that right there. Okay, so this situation right there, e to the negative of x minus 2, that is it fits the known form. That's we adjusted for the center, it has an x minus 2 in it, and that e to something that fits the known form for Maclaurin series. Where did it go? Here, e to the x. That's going to be x to the k over k factorial for all x. So here, the let's write, okay, x to the k. So negative, let me move that over. Negative of x minus 2, all that to the k over k factorial. There's our e to the negative 2, e to the negative 2. And so everything in pink there became everything in pink there. And you know what? I'm going to move that actually just for some more space. Let's put all of that down here. There we go. Okay, so finding that, oh, where did our 3 factorial? Yeah, okay. Then if we work on that power series a little bit, we would have the sum from 0 to infinity. The k here distributes to the x minus 2, but not the x and not the 2, just the x minus 2, and then to that negative 1. So we would have negative 1 to the k, e to the negative 2, x minus 2 to the k, all over k factorial. And check that out there. Let's use another color. Let's use gray. All right, that in gray is the same as what we had up there. And the added benefit of using that known form is the interval, you get that for free. The interval was all x. So with this approach over here, IOC comes along with known series. It's all X. No ratio test necessary. All right. Moving on, evaluate. I think this is our last one. Awesome. Evaluate cosine x squared, antiderivative. Okay, that has no antiderivative. So switch out cosine x squared for its power series, known power series. Okay, so again, that would be the sum k0 to infinity, -1 to the k, input, so x squared to the 2k, all over 2k factorial with a dx. All right, then before you integrate and use the power rule. Oh, hi, Sophie. Hi. Yep. Dx. Then, okay, so you integrate, keep the sum as it is, -1 to the k, x to the 4k. Here, let's do this. So you'd still have 2k factorial down there. That does not change. You got a plus c, the x to the 4k piece, this one. You do the power rule, x to the 4k plus 1 over 4k plus 1. That's what's happening. X to the 4k plus 1 over the entire new exponent. That's the power rule. Then, okay, so that piece is that. Then use it to evaluate that integral. Not estimate, but evaluate. Okay, so 0 to the 0.1 of cosine x squared dx would be its antiderivative, which we just found. Here, let's copy that actually. Let's do that. Copy. All right. And then we're going to evaluate from 0. Excuse you, Sophie. I think there we go. 0 to 0.1. The plus c would cancel out just like normal when you evaluate with a definite integral. Now we're going to take that and plug in a, here, let's do. There's that one. Let's do that again. Paste. All right, so let's keep track here. We would have 0.1 n for x, 0 n for x, we're subtracting. So that's the antiderivative evaluated at the upper limit. That's what's happening here. Minus, as always, the antiderivative evaluated at the lower limit, 0. Now all of this is 0, goes away. So we end up with just this piece. And there you go. So what we're saying is that the area under the curve from 0 to 0.1, area under cosine x squared from 0 to 0.1 is equivalent to this converging alternating series. We know it converges because of the alternating series test. It's the a sub k is decreasing, it's limiting to 0. And so this converges. Whatever it converges to, that's the evaluation of that integral. We're not going to find out what it converges to. We're going to estimate what it converges to. And in the next part, it says, using alternating series test, error bound, find the upper bound for the error, find the value that the error is the same as or less than if we estimate the integral using the first 3 terms. And here it's not telling you to estimate, but let's do that anyway. So let's estimate with the first 3 terms. So let's take the series. There we go. Okay, so we have said that 0 to 0.1 of cosine x squared dx equals that thing, which is estimated by the first three terms. So -1 to 0, 0.1 to the, if you plug in 0 for k, it's 1 over 0 factorial times 1 plus, now let's plug in k being, that was k being 0, k being 1, k being 2. Yeah, okay, those are the first three terms. So then when k is 1, you'd have -1 to the 1, 0.1 to the 5 over 2 factorial times 5 plus -1 squared, 0.1 to the 9, 4k, or sorry, 4 factorial times 9. That's the estimate. Then the question of this upper bound is telling you how close did our estimate get to the actual value, whatever it is. It's because this is an alternating series, and each term of the alternating series tells you how close you got to the actual sum, having summed the previous many terms. So if we're going to estimate the actual sum, this sum, with three terms, then it's the fourth term, the size of the fourth term, that will bound our error. So for the error bound, we need the fourth term. Fourth term, size of fourth term. So that means absolute value, or the plus version, and it would be absolute value -1. Let's write it here. So plus -1 cubed 0.1 to the 13 over 6 factorial times 13. This is when k is 3. This is our error bound. Absolute, here we go. Absolute, or like size, magnitude. Okay, so if we take that, that's 0.1 to the 13. The -1 to the 3 wouldn't matter. So 0.1 to the 13 over 6 factorial times 13. Let me figure that out. Okay, so 0.1 raised to the 13 equals that divided by parenthesis 6 factorial times 13. 6 factorial times 13 parenthesis. I got 1.07 times 10 to the -17. 1.07 times 10 to the -17. And I believe that was correct. All right. There you go, y'all. Been a real pleasure. You take care. Good luck on your exam tomorrow. And stay in touch. Y'all can do great tomorrow. Just be yourself and try to enjoy it. Really, try to enjoy it. All right.